Hello, everybody. Thank you so much for watching this presentation. My name is Sebastian Montoya. I am graduate research assistant at the Department of Civil and Environmental Engineering in the University of Maine, conducting some research under the advice of Professors Aaron Gallant and Bill Davis. Currently, we are working on the assessment of micropiles for integral wetland bridges. Today's talk is going to be about a tiny piece of the research that is concerned with the flexural strength of micropile thread joints. So let's jump into it. Micropile has several construction advantages. They can be installed through subsurface conditions that come with cobbles, boulders, caving soils, can penetrate through rock. They also require low head clearance and introduce low vibration during installation. And they are used to stabilize slopes, support integral abutment bridges, support offshore structures, and many other applications that impose bending loads on these elements. So the question is, for a substantial bending loading, is the joint strength going to be enough for an adequate performance of the foundation system? So if we take a look on the micropile, they are composed of segments, which are typically 5 to 10 feet long. In one of the ends of each segment, there's a box end, and the other is what we call the pin end. Both of them match so that the joint can be created and the stress transfer can be attained. And this joint is typically 2 to 5 inch in length. So we think about a very tiny joint, and it's not surprised it ends by failing. Indeed, in the literature, we have identified two failure modes. One of them is called jump out, that is shown and schematized in the figures in the left, and the other is rupture, that is schematized by the figures in the right. So during jump out, what it's happened is that there are some radial deformation of the box end, that means it's dilating, that reduce the contact in between the threads until they're no longer in contact, and that makes the connection to the couple. On the other hand, for rupture, what happened is that due to imperfection, area reduction, stress concentrations, we develop a crack. And once that crack propagates, rupture of the joint takes place, and then no longer bending capacity is possible. So these failure modes take place in a brittle way, and for bending loads that are much smaller than the gross section capacity. And here gross section, we refer to the pipe, intact pipe itself without the joint. We look for some advice on how to consider this source of structural weakness into the design. Probably one of the few we are going to find comes from the FHWA. They state as a conservative approach that consists to assume that the wall thickness in the joint is just 50% of the intact casing thickness. So if we look in the figure on the right, this recommendation means is that the gross section is shown by the blue area. For design purpose at the joint, we are going to consider only the red area. It's just 50% of that. But is this recommendation considering any failure mode? How it's accounting for the thread details, for the thread size, thread shape, thread length? All these variables influence on what the joint capacity will be and what the failure mode will be. So we look historically at it. These two failure modes were first identified on drilling pipes used on oil and gas industry. Findings present a analytical expression for what the jump out and rupture loads are on thread joints that are subject to pure tension. Now, Musamon et al. It can extend this work of findings to bending loading scenarios. And for doing so, they assume unconventional strain distribution and a shift in the neutral axis. And those recommendations were based on experimental 4-point bending tests that they performed on only 2 micropile types. So there's a question is this methodology proposed by Musselman applicable for any other type of micropiles, any other type of thread details and connections? And that's what we tried to address through this presentation. So let's first review the Musselman model. The first assumption is what they call the effective cross-section. Now, instead of reducing the thickness through the wall joint, we are going just to do that for the region of the joint that is subject to tension. So for compression, we are going to consider full thickness, but for tension, we are going to consider only a fraction of that thickness. And this recommendation is based on the fact that during bending, the threads that are in the side of the compression are attaining full contact, but in the tension side, the threads slip one over the other. That reduce the contact in between the threads, and an easy way to account for that is just reducing the thickness. Then, second assumption was the non-conventional strain distribution. And based on their observations, they described a linear strain distribution that is shown here in the figure B. Is described as essentially linear in compression and almost constant in tension. Now we can introduce here what the failure mode is. If in tension we assume the corresponding strain to jump out, that's subscript J, or rupture, that's subscript U. If we have a constitutive law, for instance, an elastic plastic relationship for steel, we can translate strains into stresses. So in tension, we'll have the corresponding jump out or rupture stress, depending on what the failure mode is. And for compression, we have to solve what the compression stresses are so that we accomplish equilibrium. That means no axial force are applied or resultant tension equals the resultant in compression. And if we attain that condition of equilibrium, we now know what the stress distribution are, and we can compute what the bending moment at failure is in the joint. Now, the only ingredients we need for this recipe are the rupture stress and the jump out stress. Rupture is easy. That comes from elemental testing. A coupon test, that will be the ultimate tensile capacity. But what about jump out? The only we have available is the expression developed by Clandins for pure tension. And that's what we have here. Now, Clandins what he did was relate the axial stresses on a pipe that will induce jump out for a given geometry, considering also the circumferential or hoop stresses that are developed in the pipe. Then that's what the equation presents here. Although it seems complex, can be decomposed in very simple pieces. In the numerator, we have a nonlinear axial stress that is relating the yielding and tailhand capacity to the strains through parameters A and B. Now what we have inside the parentheses in there, 2H over D. H here is the thread size. D is the pipe diameter. So we are talking here about the jump out strain. And in the numerator, we have tan alpha minus E. Alpha is the inclination of the threads, and C is friction angle. So this is essentially introducing friction among the threads. And we have some relational terms that is accounting just for the circumferential stress. And we have all we need to estimate bending capacity and the thread connection. That's what we did. We performed a model assessment by comparing the predictions with observation on 46 tests reported in the literature. 43 of them were 4-point bending tests performed at laboratories, and 3 of them were field pushover tests. And they were spanning over a wide range of pipe diameters, wall thickness, and different connection types with different thread geometry. For instance, we have what we call the US connection type. That's a pin box connection with triangular threads, and Euro one, that it's pin box connection, but with square threads. And similarly, an Euro 2, there is a pin connection with square threads and an external couple. So those are our results. In the vertical axis, we show our prediction of thread joint capacity versus in the horizontal, the observations of the thread joint capacity. First thing to know here is that we group the 46 tests into 13 different types, depending on that each type has in common diameters and same geometry and material properties. So note that P1 tests, those are the field tests. For field, you cannot really measure what the bending moment is at the joint of failure. What you can measure are strains and displacement. So what we have reported here are results from a final element analysis back calibrated with these measured strains and deformations. So these observations carry some considerable uncertainty. Now, second note to hear here is that we have some clustering data that I highlight here by the red box and the blue box. Red box is enclosing all the tests that fail in rupture, while the blue box is enclosing all the tests that fail in jump out. Now, note that all the ones that fail in jump out are US connection types, triangular threads, while rupture, with the exception of one test, all of them correspond to Euro connection types. So that means square threads fail in rupture, triangular threads fail in jump out. Only one of the triangular threads fail in rupture. That's point P13, and that was only because it has a higher thread length that will be L here in the sketch. So at first we can think, okay, jump out produce higher moment capacities than rupture, but that's not necessarily true. Indeed, what's happening is that we have higher diameters at the top while smaller diameters at the bottom. So for instance, P13, that's the highest diameter we have, that's 246 millimeters versus P6, that's the smallest specimen, that's just 89 millimeters. So we are going from smaller diameters and smaller capacity to higher diameters and higher capacity. Now, skills of the method are really nice. Correlation between prediction and observation are 0.98, and the mean square root error is just 21 kilonewton meter. That if we consider the order of magnitude of observation, there is thousands of kilonewton meter. It means a very small error. We normalize the same results by the yielding moment of the gross section, we can appreciate what the strength reduction was at the joint. And that's what we present here again. Exactly same data, just that normalized by the yielding moment. So we have the ratio between the moment of failure in the joint versus the moment, the yielding moment of the gross section. And now we know that the clustering changed. Now we have jump out at the bottom and rupture at the top. That means jump out is attaining the smallest strain ratio among all the specimens, where the rupture is attaining the highest one. Jump out, it's on average on observation about 0.3. That means we have a 70% in a strength reduction for triangular threads or failures in jump out, while rupture, you can attain up to 90% of the cross section capacity. Something else to note here is that we plot the 50% recommendation that's say here the 50% rule, that is to reduce the thickness of the pipe to 50% according to FHWA. That's shown here by the dashed line that produces exactly 0.5 in strength ratio according to this equation. And what it's more important to know is that several specimens fall below that recommendation, attaining less than 50% capacity. That means this recommendation is not always conservative. And something to keep in mind, also the message here is you have to coin for the thread details if you want to assess a conservative approach. Otherwise, you could be in an unsafe design. Summary, I want to say again, 50% thickness reduction is not always conservative. Second, the most influential parameter governing the failure mode was found to be the thread shape. Third, the geometric details can be optimized during milling process to ensure that rupture controls, and in that way get the highest capacity. And lastly, the present model provides a tool for prediction of flexural capacity of a thread joint, and potential benefits of that include that we can design the thread so that we can optimize the milling process. Additionally, we can have substantial savings in structural testing, as of today, the only way to know what the capacity of the joint is to test, to perform a test. Some potential future work will include the effect of axial load, as micropiles are subject to axial load as well, simultaneous to bending. Second will be to address the influence of a central reinforcing bar. So since we are predicting a shift of the neutral axis, even a bar located in the center of the section will contribute to bending capacity. The third point will be study the consequence of failure. What will be the super and substructure performance when the thread joint fails? And last will be address an experimental program to validate the strain distribution for a wide range of pipe and thread details. We want to acknowledge the financial support from the Maine Department of Transportation, the assistance and advice of Mr. Dale Peabody, Laura Krasinski, and Garth Gustafson, and also the financial support provided by the Transportation Infrastructure and Durability Center. If you have any question, I would be very happy to answer them. Thank you.